everyone. I'm Lucas from Trendmichael, and this presentation is the story of my fuzzing tool, and I finished it in 2017. And I used the tool to find bugs on Windows platform over a year. Okay, here is my introduction. I'm a security researcher from Trendmichael, and I'm interested in vulnerability discovery and binary exploitation and reverse engineering and symbolic execution. And in recent years, I target on Windows platform and report bugs to MSRC. And if I have free time, I would like to play CTF games with my team members, and we are from Hikon CTF team. So here is the agenda for today. Motivation mentioned the reason that why I create this tool and talk about some related works. And my work is based on American fuzzy loop, so some related background is here. And implementation detail what I have done. And the focus of this presentation is high performance, so some simple benchmarking data here, and demonstration. And for the case study part, I only focus on the Windows kernel and driver. For the user mode application, I think another tool, such as WinAFL, have covered it already, so I will not talk too much about the user mode case. And the conclusion is at the end. So AFL is a very great and famous fuzzer. Many cases and data have proof about it. And I want to use it on the Windows platform, but it does not support Windows. And the main reason is that most of the Windows application is closed source. 2 years later, and someone from Google port the AFL to Windows, and that is the WinAFL project. And it used the dynamic binary instrumentation to get the code coverage, so it doesn't need the source code of the target application. However, it slowed down the speed on fuzzing, and I hope it can fuzz the kernel driver. At that time, I think static binary instrumentation is one of the solutions to achieve these two requirements. And yes, I know about the project CCG. I'm not sure about the pronunciation. And it does the static binary instrumentation on Chrome browser and optimize the binary execution on the Windows platform. I surveyed about it, but it requires full symbol, which include the profile information of the target application. So I give up here. And I hope I was working in Microsoft so that I can get the symbols. Later, someone from Microsoft wants to do the similar thing and port the project CCG into the WinAFL. And I know the solution from Cisco, it is based on the Intel processor trace, but it is still in progress at that time, and it cannot be scaled up on the virtual machine. And some other feature I still want to have. So people always said, you only know how to say, why not do it yourself? So I finished it what I want. And here is some related works in static, and WinAFL is the project that just mentioned before. And the limitation is that it requires the full symbol of the target application. And here shows that the tool of static binary instrumentation on PE format is still not available, or limited by some condition. And here is the related works in dynamic and DuckO I suppose it is the sub-project from Capstone, and they have presented on some conference, and that is the only information. And it used the Capstone to finish the static analysis and use the keystone to rewrite the binary at runtime. Benefit from Capstone and Keystone, it is cross-platform and architecture, but the project did not open source. And KFast is another interesting project. The information is from a blog post only, and it mainly focuses on Windows kernel driver. And it rewrites the driver and install the hook for each basic block in runtime to feedback the call coverage. And the hook is a long jump with 5 bytes. Actually, if the basic block is smaller than 5 bytes, then there is a problem. So it used the interrupt instead of the hook and install the interrupt handler to solve this problem. There is a small performance penalty here, but I think this is still a smart solution. Okay. And here is a related work on hardware support, and most of the solution is based on the Intel processor trace, and which is a hardware feature from the new generation Intel CPU. And WinAFL Intel PT is a project from Cisco, and the project was presented on many conferences, and they developed the Intel PT driver on Windows platform, and for the recent, for the current version, they directly use the built-in Intel PT driver in RS5. But it does not work in virtual machine currently. And Pe-afl is an academic project, and it combines the QEMU, KVM, and Intel PT, so it can scale up and with virtual machines and cross-platform. It also can filter the PT trace data with specific virtual machine or user mode or kernel mode, PID or EIP. So Intel PT is a robust feature, but it cannot finish some feature which I will explain later. And here is the solution for virtualization and Apple Pie. Apple Pie is a very new project. It came out when I was preparing this slide. It combines the box and the Windows hypervisor platform API. So it gets the call coverage at the hypervisor level rather than the emulation level. So the performance is improved a lot. It also supports a fast reset, which restores the snapshot with the modified page only. And here is the picture to explain the AFL, and one picture is better than thousands of works. And at the beginning, it is the initial sample set as input and start the loop. And then AFL choose one input from the queue and mutate it. And then it runs the target application with the mutated input. If it generates a new call coverage, then it saves the mutated input into the queue. Otherwise, drop it and loop again until it gets the crash and hang. So the key point here is the coverage. And AFL instrument some assembly code at the beginning of each basic block during compile time. And the assembly code is used to record the code coverage during execution time and save it in the bitmap. Then AFL can collect the code coverage from the bitmap directly. For the Windows application, we usually don't have the source code. So we cannot instrument the assembly code during the compile time. However, we still can instrument the assembly code statically. It is quite straightforward, but there is a lot of work to do, not only on the assembly code, but also on the PE format. I named this project as pe-afl. And for the assembly code, the instrument code expands the original code, so some of the jump have to update their new relative address. And even some of the jump have to change from short jump to long jump if it is necessary. And sometimes the instruction size becomes larger. And for the PE file format, and the first thing I do is to duplicate the executable section and instrument the code on the new section. And some data, such as import table, still remains on the original section. It is possible to remove the original section completely, but I think it is in the future work. And then I append a new section, .coverage, to save the coverage bitmap and some variable that I used. Then P header and some related tables have to update, such as section table, export table, SEH handle table, and relocation table. And most of the update is from old address to the new one. And the picture on the right-hand side shows the before and after. And the yellow part is the update, and the green part is the append part. And all the information that I need is extracted from the IDA, such as basic block, branch, and its target address, and OP code, and operand, and StackFrame. Since it is static analysis from IDA, some of the information may be incorrect and lead to some issue. I will detail those issues later. But first, I will have to talk about why I need the StackFrame. And here is the reason why I need the information of StackFrame. It can be used to poison the StackFrame at the beginning of each function, and the stack is initialized with some magic value. It can use that to detect an initialized stack variable or memory leak from stack. And this is a case to apply the static binary instrumentation not only on fuzzing, but also on bug detection. And I think the solution based on the Intel process trace cannot do this kind of feature. And unfortunately, Microsoft put some nice mitigation on the Windows kernel stack. It kills the related bug class. But it looks like it covers the POD structure on the stack only. And it did not cover the user mode application, so it seems still effective on some specific situation. And I just mentioned that there is some issue due to the incorrect static information from IDA. And that is the challenge of static binary instrumentation on PE file. All the incorrect information is because the data and the code are mixed together in the executable section. For example, an Unicode string argument in Win32 API have to align to 2 bytes. Otherwise, the API will return error. And the exception handler table, SEH handler table, have to align to 4 bytes. Otherwise, the PE file format is invalid and it cannot be executed. So we need some extra work to take care about the data alignment on the executable section. Anyway, this kind of alignment problem is easy to solve. But here is another kind of problem, and it is hard to be solved. And that is the confusion between the code and the data. Sometimes IDA may assume the data as code, or assume the code as data. For example, a string argument ABC here, which is in the executable section, and it is incorrectly assumed as code. After that, the code is instrument, and actually, it is corrupting the original data. This leads to the incorrect API argument, and the different behavior between the original one and the update binary. On the other hand, if there is a branch in the code, and the code is assumed as data incorrectly, and we will not update the branch and its related address. So after that, the execution may fail in here, and because the branch jumped to the old related address, but not the new one. Sometimes it is difficult to identify if whether a binary data is code or data. The problem is similar to the picture on the right-hand side. It is difficult to identify a picture whether it is a Chihuahua or move-in. For this kind of problem, if you have the public symbol for the binary, and it provides the reliable information about which is data and which is code, and so the problem is solved. Otherwise, if you don't have the public symbol, and you can wait for the update version of your IDA Pro, as I see some case in the old version is fixed in the new version. And so they are improving, but very, very slow. And otherwise, if you don't have the public symbol and the disassembler have something wrong here, give it a try to fix the issue. For the case that assumed data as code, I instrument before the branch instead of the basic block. And then I validate the target of the branch. If it is invalid, then I alert them and fix it manually. And for the case that assumed code as data, I try to look for a valid branch in the subspecies data, and which is usually located at the end of a function. And some of the known data type can be filtered. Then I alert the remaining subspecies data and also fix it manually. The strategy here is semi-automation. Honestly, the solution here did not cover all the corner case, and some of the case can still be missed. And I did not put too much time on here to figure out a better solution. Maybe some simple emulation can be used here, or maybe some academic solution is available. It still has a room for improvement. And here is an example for instrumenting msping.exe without the symbol. As you can see, there is some warning message while collecting information from IDA. And that is the list of the possible confusion between the data and the code. And honestly, this is not a good workaround. And here is a picture to describe the fuzzing scenario. The scenario is similar to AFL. There is a wrapper test wrapper.exe. It is used to load and execute the target library, which to be fast. And named pipe and share memory is used to communicate between the wrapper and the fuzzer. After finishing one execution, And wrapper copy the coverage bitmap from dot coverage section to the shared memory. And then the fuzzer can get the code coverage. For the kernel mode fuzzing, the scenario is similar. A helper driver is used to finish some job, such as mapping the dot coverage section into the user mode. Then the wrapper can access the dot coverage section directly. And he mentioned different type of instrument that you can use on fuzzing. For kernel mode fuzzing, PID filtering is usually used to ignore those unnecessary code coverage from another process. And for user mode fuzzing, some of the application is multi-thread, and so I allocate different AFL previous location variable for each thread. So the coverage is keep deterministic under the multi-thread environment. And usually you instrument the assembly code directly with inline mode for performance purpose. Also, you can instrument the C code for each basic block to finish some complicated task. So you don't need to deal with the low-level assembly and the relocation. And the choice depends on your requirement. And here is some benchmarking data. And the benchmark is based on fuzzing the GDI Plus library. And the environment is on Windows 10 virtual machine with 4 GB memory and i7 CPU with 1 core. As you see, the speed is close to the native execution, and it's speed up around 2 times over WinAFL. And WinAFL states that the overhead is around 2 times over the native execution. Our benchmarking data here shows it is close to the statement what is said. And here is the demonstration. Can you switch the screen? Okay. And here is the demo driver, and here is the source code. Let me see the source code first. Okay. User mode application can use the L control to call this function, trigger demo here. And here is the user mode input buffer from here. And then there is lots of if statement here. And it checks the input, user mode input buffer with the BlueHat, BlueHat here. And I put a bug check here, 1337. So if the input buffer passed the first 4 if statement, then the system will crash and got the blue screen. So now, start your IDA. And analyze the demo driver here. I instrument it without the symbol, so I choose no. And use the script to dump the static information here. And here is some highlight. the highlight is represent the basic block location here. And then there should be a dump file here. Little bit small. And now you can do the instrumentation. Oh. The size is too small. Okay. And now you can use the pe-afl with the demo driver and the dump file that you just create. And there should be an output. Oh, because the performance of this notebook is very bad. And the output is here. And as you can see, the size becomes larger. And now you can copy this update binary into the virtual machine and ready to fuzz. Actually, I already copied it in here. Oh, the screen is a little bit small. And what you have to do now is stop the demo service and override the original demo driver with the update binary, and then restart the demo service here. And then you can try to fuzz here. Oh, the command is too small. I think the command should be and -i is the input directory, and you can check the input directory here. I only have one input, and it only contains 4 character AAAA. And the -o is for output directory, and -p is the target driver that you fuzz. And test out control here is the wrapper that try to do the memory map and create a device demo. And I specific the out control code here for the demo's purpose. In the real world case, you can generalize here. And the last one is the input pass. So after you execute it, and maybe wait around 10 seconds, because the resource for this virtual machine is very limited. And the speed is around 115 around per second. So here is the stop code. Oh, the stop code is too small here, 1337. Sorry about that. And now we can switch back to the slide. And here is the first case study. And CLFS is the first try on Windows kernel driver. It is a well-known attack vector and fully researched by Project Zero, Kin Team, and Chihu 360. It is also used on some competitions such as Pom2On, By the way, it was sandboxed recent years. The driver passed the undocumented pe-afl format in kernel, so it sounds very dangerous. And the entry point is from the API create transaction manager. And the pe-afl format has checksum, so I patched the checksum in the driver manually. And then I applied the pe-afl and fuzz it on 8 virtual machines about 2 weeks, and finally deduplicate some crash and send them to MSRC, and 2 CV is assigned. And one is poor overflow, and another one is use after free. And by the way, some of the crash POC did not fix. So those case becomes the anti-fuzz case on my fuzzing tool. And the second target is the CNG driver, which is one of the well-known vulnerable driver. And some of the entry point is from I/O control. This scenario is also applicable on any kind of I/O fuzzing. When the fuzzer start, the core coverage did not increase rapidly and stuck. It doesn't make sense based on the complexity of the driver. So it's time to figure out the root cause. And benefit from the static binary instrumentation, and it is easy to dump the execution trace and see what happened. Also, you can import the trace into the Lighthouse, which is an open source IDA plugin, and show some statistics in the IDA. It is more convenient on reverse engineering or debugging. Okay. And after some investigation, the input for the I/O control needs some valid object, such as event object and the magic header. And after that, I slightly adjust the mutator and the input, and finally the core coverage increased. And after fuzzing a week on 8 virtual machines, the result is 1 CV, and that is in out-of-bound read on poor memory. And the third case study is registry Hive file. The registry Hive format is undocumented and is passed in the NTOS kernel. The entry point here is from the reg-row app key. And this time, we have to instrument the NTOS kernel, which is a very large executable, around 7 megabytes. It doesn't make sense to instrument the whole NTOS kernel, so we partially instrument the code that we only concern. As you can see in the picture, the NTOS kernel is partially instrument with some regular expression matching. The match is on the symbol's name. So, however, no result at the end. And one possible reason is that the global state of registry in NTOS kernel has changed frequently. And the fuzzer runs as persistent mode, so one input registry file may produce different core coverage. And it affects the stability and the effectiveness on fuzzing. Maybe we have to partially instrument the parser code more specifically. And here is a post story about instrumenting NTOS kernel. And is it possible to fully instrument the whole NTOS kernel and boot the operating system up? And I tried. and everything works except one place. And there is a self-modifying branch in NTOS kernel, and it is updated at runtime, and it is quite interesting that the read-only text section is modified at runtime. I'm not sure if it break any kind of security policy. And the self-modifying code is detectable from IDA. And then we can skip it with partial instrumentation. But actually, it is just a workaround to skip it and did not really solve the issue. And this is one of the limitations on static binary instrumentation. And here is the conclusion. And we show the possibility and limitation of static binary instrumentation on PE format and fuzzing. What it can instrument and what it cannot. And the challenge is mainly from the mix of data and code on the executable section. If you don't have the public symbol, and that would be a problem. Honestly, if you are looking for a reliable or elegant solution, I think static binary instrumentation is not your choice. But it works in high performance and benefits from the static binary instrumentation, and the fuzzer can be improved. So code coverage is not only the thing that you can feedback, so you can also feedback the data or memory access or stack diff or anything you want. And the static binary instrumentation is not only for fuzzing, it is also applicable on bug detection or execution tracing. And I will release the source code as soon as possible if there is no any other concern. And the static binary instrumentation part can be reused in many purposes. And I hope it can benefit to someone or got something from here. And especially, there is still many attack vector, and they did not test. And I have to say thank you for the AFL, WinAFL project, and some people here, and especially for the BlueHat conference team. And here is my contact information. And if you have the question, you can message me directly. And